Hey, wow, I'm so happy to see you guys here. Sorry for the unfortunate timing and whatnot, but I'm really glad to see that some of you guys were able to make it to this afternoon meeting instead. Just a heads up, it is possible that I get a call from the vet while this is going on. So if that happens, I'll pause the recording, figure out what to do, and then let you guys know before we pick back up. Yeah, me too, man. He's an old dog, and you never know when something like that happens. It could be a sign of something serious, but hopefully it's not. The vet triaged him as non-emergency, and that's why they've been taking so long. So it looks like at least it's not something that requires serious immediate attention, but thank you. I appreciate the concern. And make sure the recording is going good. All right. Yeah, Matt. So I actually, about an hour and a half ago, I went in and cleared all of the extension requests that were up in WebAssign. So if you had a request that you submitted earlier, it should be taken care of. If you submitted it in the last hour or so, then I will not have granted those yet. But I can take a quick look right now to make sure you can get in and see things. Come on. Does look like I got a few more in the last few minutes here, so let's knock these out. Pause the rec up. All right, we're back, and we can start working on some mathematics. So this is Calc 2. And today is the 3rd of August, which means we are dangerously close to the end. There's two little topics that I like to use to round out the end of the semester with Calc 2. And these are parametric equations and polar coordinates, which are both things that you see in pre-calculus and trigonometry respectively, but you only ever do the graphing and the algebra there. You don't do any calculus with those objects. So here we're going to learn going to revisit two topics from trig and pre-calc, polar curves or polar coordinates, and parametric curves. There's 4 sections in the textbook altogether relating to these, but 2 of them are just little like recaps of the stuff that you learned in trig and pre-calc. I don't want to pretend like everybody remembers everything from that class, so I will do a quick touch on 10.1 and 10.3, which are the introductions to parametric curves and the introduction to polar coordinates. But then the main stuff here is that we're going to do calculus. We're going to learn how to do calculus in these settings. So the polar coordinate stuff, I believe, is 10.3 and 10.4, and the parametric curve stuff, I believe, is 10.1 and 10.2. Let me make sure I'm getting that right. Yeah, so this is 10.1 and 10.2. And this is 10.3 and 10.4. So 10.1 is your like intro to parametric curves, remind you of the stuff you learned in pre-calc. 10.2 is calculus with parametric curves. 10.3 is intro to polar coordinates, stuff that reminds you of what you did in trig, and 10.4 is calculus in polar coordinates. We're going to move very quickly through 10.1 and 10.3, and we'll slow down a little bit in 10.2 and 10.4. So let's start on section 10.1. This is the intro to parametric curves. So in calculus, we deal a lot with curves, but usually the curves we're looking at come from functions. right? Where y is f of x, or sometimes, maybe x is g of y or something like that. But usually the curves either pass like the vertical line test or the horizontal line test. Usually one of the variables is a function of the other. But many curves are not like that. So our starting observation, many plane, meaning like live in the plane curves, do not satisfy either y equals f of x, nor x equals, say, g of y. All right, so neither variable is a function of the other. It's a g. For example, maybe you can imagine that I drop a little ant down on the page, and I imagine that ant's holding a little paintbrush, and I just let him wander all over the page. He could follow some sort of crazy ass path like this, right? Maybe I pick him up here and I set him down here. This certainly does not express y as a function of x because it fails the vertical line test all over the place. And it also does not express x as a function of y. It fails the horizontal line test. So remember, we're imagining I dropped the ant down here, so I'd say maybe this is at time t equals 0. Or let's be more general, let's say time t equals a, some starting time. And over here is where I pick the ant up off the page, so we'll call that time t equals b. Our goal is to get to a place where we can do all of the nice calculus things that we like to do with curves like this, even though y is not a function of x. And the trick to doing that is to think about this other variable that I've so sneakily just dropped in there called t. And then I imagine this path is being traced by a point moving around on the page, like our ant, just maybe walking around, over time. So at some time I set him down, he wanders through the plane like this, and then over here I pick him back up. The main idea is that if you take any point along this graph, along this curve, it definitely has an x and a y, but I think of x as being a function of time, changing independently on its own from y, which is also a function of time. So instead of having x be a function of y or y be a function of x, I think of both of them as being functions of some third variable. Usually we use t for that because the analogy with time and motion is so convenient. So this would be an example of a parametric curve, and the parametric equations usually look like, x equals x of t, some function of t, and y equals y of t. So I'd have like x equals sine t, y equals cos t, or something like that. And then also, it's understood that t is allowed to run from A to B. So this is kind of your time domain, and these are your parametric equations. And the equations together with the choice of t is what determines your curve. So I'll show you lots of examples. There's lots of ways to graph these. You can always do the thing that you do in your baby algebra classes where you make a big table, right? You plug in a bunch of t values, you get a bunch of points out, you graph those points, and then we'll see some slightly more grown-up ways to go about it. But the main idea here is that neither variable is a function of the other. X is not a function of y, and y is not a function of x. So we can get much more exotic shapes out of these things. They don't need to pass either horizontal or vertical line tests. All right, so we're going to solve the tangent problem, right? We'll be able to find slopes of tangent lines. We're going to solve the area problem. We're going to solve a new problem called arc length in this setting. But first, a little bit of practice graphing. Let's sketch the graph of the parametric equations. How about x equals t squared minus 4 and y equals t plus 1, where let's say t runs from like negative, how about -5 is less than or equal to t is less than or equal to 5. So the idea is I can figure out x values by plugging t's in here, and I figure out the y value associated with that x by plugging that same t in here. So separate equations for x and y, but the same sort of thing that you're used to from algebra, and if you don't know what else to do, you make a table. So I'll have a t, an x, and a y in my table. And we'll do like -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. I'll probably skip a few of these. I'll look and see which ones are easy to compute, and we'll go from there. All right, but these are the whole numbers that are in the time interval I'm considering, -5 to 5. And then each row will give me an ordered pair that's on the graph, just like your normal tables. If I plug in -5 for t, x of -5 is -5 squared, which is 25, minus 4. So that would be 21. And y would be -5 plus 1, which would be -4. If I plug in -4 for t, x would be -4 squared minus 4 is 16 minus 4 is 12. And -4 plus 1, y here would be -3. I'll keep going, -3, that would be 9 minus 4 is 5. And -3 plus 1 is -2. If I plug in -2 for t, then this will be 0, right? I'll have -2 squared, which is 4, minus 4 is 0. And -2 plus 1 is -1. If I plugged in 1 for t, I would get 1 squared, -1 squared minus 4, which is -3. And then down here, I would have -1 plus 1, which is 0. If I plug in 0 for t, I get -4 for x and 1 for y. If I plug in 1 for t, I get -3 for x and 2 for y. If I plug in 2 for t, I'll get 0 for x again. And this time I'll get 3 for y. If I plug in 3 for t, in fact, there's symmetry here, right? If you follow this down, down to here, then you can start chasing it back up. So the next fellow here is probably going to, let's see, if I plug in 3, then this would be 9 minus 4 is 5. So we're back to that x value. And if I plug in 3 for t here, I'll get 4. I feel like I have plenty of points now. So let's start drawing a graph. All right. So when t is -5, x was all the way out at 21. So let me call this 20 here. And y was down at -4. Well, my y values seem to be relatively contained. So let's call this -4. Let's call same distance up here +4. If that's 20, then 10 is like right here. And we can do a reasonable job graphing things from that. So this row tells me that the point 21, -4 is on my graph. So that would be right here. That's the point I get from the first row. And then I've got 12, -3. So if that's 4, this would be 2, 1, 3. So 12 comma negative 3, well, that should be a little bit to the left of, or a little bit to the right of 10, and right like down here. So say 10, 15, 12 should be like here. Something like that. Yeah, that looks about right. So this guy is 12 comma negative 3. And then if I keep going, I get 5 comma negative 2. So 5 would be here, negative 2 is right here. Zero comma negative 1. So when x is 0, y is negative 1. That's my y-intercept there. Negative 3 comma 0. So if I continue the scale the same way on the other side, there. This is like negative 10. So negative 3 comma 0 should be, well, that would be 5. Negative 3 comma 0 should be like right here. And then what do we have next? Negative 4 comma 1. So that would be here. And then we'll have 3 comma 3. Sorry, negative 3 comma 3. Which is like here. All right, negative 3 comma 3. That came from t equals 1, right? Negative 3 comma, oh, negative 3 comma 2, sorry. So negative 3 comma 2 would be right here. That's this row. And then we had 0 comma 3. And then we had 5 comma 4. We're all the way back up there. So 5 comma 4 is right here. And if we carry this all the way down, when t is equal to positive 5, we would have 25 minus 4, which is 21 again. And we would have 5 plus 1, which is 6. So my last point would be, that look about right? Yeah. 21 comma 6. So this was my starting point. And my little ant is walking from dot to dot in order as t increases through these points. And the curve, you can see this is tracing. This looks like a parabola. And it is. It doesn't continue forever and ever in that direction because t begins at negative 5 and ends at positive 5. If t was allowed to run from negative infinity to infinity, then it would continue on in that direction. But here we're given a restricted time domain. So we start over there. And we finish over here. Nice big fat points. These parametric curves, so this is a sideways parabola. Right, that's the graph we get out of this. And we just got it by making a table. These parametric curves have what's called an orientation. There's a direction that they're being traveled. So again, think of the ant walking around on the page. I set the ant down here, and I picked him back up here. And as t ran from negative 5 to 5, the ant walked along this path from this point to this point. The starting point is sometimes called the initial point. And the ending point is sometimes called the terminal point. This guy was associated with t equals negative 5, and this guy was associated with t equals positive 5. So this is how we graph parametric curves. It's not terribly hard. Yeah, Simon asked a good question. Where is t represented in this graph? It's not. T is not represented anywhere in this graph. This is the x-axis. This is the y-axis. There is no t-axis. And that's one of the first things that people have a hard time with when it comes to these, is that you're used to thinking of your independent variable as being one of the geometric coordinates, but it's not. It's not anymore. Now your independent variable is just measuring time. So you don't see him represented graphically. And there are other ways to parametrize any given curve. So we don't actually want to see t represented anywhere graphically. One of the problems we would like to be able to solve is finding the location of this vertical tangent, or finding the area bounded by this curve or some part of this curve. And that's what we'll be doing in 10.2. Any questions on where we got this graph or any of the language here? All right, so I just made a table of points, same sort of thing that you did in your algebra classes. And then I strung them together with a nice curve. The orientation is important. So when you draw these, make sure you include the arrows. There are some problems where your answer will come out negative or something weird like that if you have the orientation backwards. And for differential geometry, orientation is a big deal. We'll do one more example where we just sketch the curve, and then we're going to start talking about calculus. Let's do 2 cos t and y equals, how about just old-fashioned sine t? And here we'll let t run from 0 to 2 pi. Yeah, so time can be negative, right? For example, right now, it is 4:51 and 40 seconds, and you sent that message at 4:51, so you sent that message at t equals negative 40 seconds from this perspective. So time being negative isn't necessarily an unreasonable thing, it just means earlier. And remember, the analogy with time is just that, it's an analogy. It's not like t must represent time, it's just that that's one of the easier ways of thinking about this. So time is, as far as we know, like a one-dimensional thing. And you can move forwards and backwards along it, at least in theory. We can't, right? We're bound to all the laws of physics and stuff, but the mathematics works great. Newtonian mechanics works fine when you run stuff backwards and forwards. So there's no problem with negative times here. And if you don't like that, then you can think of t as representing just anything. Like, it doesn't need to have any physical representation. It's just a parameter. That's where the term parametric comes from. T is just a parameter. I can't, no, I'm really good at time traveling forwards, but back is tough, and I don't have a whole lot of control over the speed forwards. But, we'll get there one day. So how do I graph this thing? I could make a table. That's an option. We'll do that real quick. I'm not going to use as many points here as we did last time because I'm lazy. But I also want to show you another way to do it, called eliminating the parameters. So let's look at like t equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. If I plug in 0 for t, then x is 2 times the cosine of 0, which is 2, because the cosine of 0 is 1, and y is 0. If I plug in pi over 2, cos of pi over 2 is 0, so 2 times 0 is 0. And the sine of pi over 2 is 1. If I plug in pi, the cosine of pi is negative 1, so x will be negative 2. And sine of pi is 0 again. If I plug in 3 pi over 2, cos of 3 pi over 2 is 0, so 2 times 0 is 0. Sine of 3 pi over 2 is negative 1. And at 2 pi, we get the same thing as we do at 0, because these are both periodic with period 2 pi. So here I've got some points. And there's a few interesting things that have happened. So first I'll plot the points I've got. This guy gives me the point 2, 0. So that would be my initial or starting point. And then I go up to 0, 1. And then I'm at -2, 0. And then I'm at 0, -1. And then we're back around here again. So my shape looks like this. And you might recognize that as an ellipse. Or at least it looks like an ellipse. Modulo my bad art, right? Of course, this little like wobble here is just me being bad at drawing. But I'd like to know for sure what this thing is. And similarly, in the last problem, it looked like a parabola, but I'd like to know for sure that it is exactly a parabola. So what I would like to do is find the regular equation. Can I find the normal, usual word for this is Cartesian, or XY equation for this curve? So right now I have these two equations involving x and t and y and t, but I don't have my normal xy equation. Remember that the normal equation for an ellipse centered at the origin is x squared over a squared plus y squared over b squared equals 1. So I would like to somehow get something like that out of these. And the nice observation is that since x is 2 cos t, we know that x over 2 is equal to cos t. And we know that sine squared t plus, I'll rewrite it down here. Also, we know that cos squared t plus sine squared t, that's always 1. So here I've got cos t, sine t is just y, so this is the same as saying cos t, that's x over 2, so cos squared, that's x over 2 all squared, plus sine t, well that's y, so y squared is equal to 1. In other words, whatever curve comes from these two parametric equations, all the points on that curve have to satisfy this equation, which we could write as x squared over 4 plus y squared over 1 equals 1, which is the standard equation, standard form of the equation for an ellipse centered at the origin, with major axis, or, with these vertices and everything as they are. So another way I could have gotten this graph is by first finding this equation and then just graphing this equation, which is something that we remember to do. We remember how to do from our study of conics. Sometimes it's easier to see from the parametric equations what your curve is going to look like. Sometimes it's easier to see from the regular xy Cartesian equation. And usually we want to be able to go back and forth from one to the other. This process where we go from the t's to the not having any t's is called eliminating the parameter t, because, you know, we went from having t's to not having t's. So we eliminated the t's. There's lots of ways to do this. Sometimes you can do it by solving the original equations for t and plugging into the other guy. If your parametric equations involve trig functions, usually you're going to want to use some flavor of this identity. Let's do one more. This time I'm not going to bother with the table. Okay. Let's sketch x equals t plus 1 and y equals t squared, where, let's say, -2 is less than or equal to t is less than or equal to 2. Why not? So I want to do this without making a table. So I want to eliminate the parameter. One way to do that is to use trig identities like we did in the previous example. Another way to do that is by solving one of the equations for t and then plugging that in to the other equation. So here I have x equals t plus 1, which implies that x minus 1 is equal to t. So y is t squared means the same as saying y is equal to x minus 1 squared. Therefore, my curve is made up of points which satisfy y equals x minus 1 squared. And I know what that graph looks like. I take your regular y equals x squared parabola and I shift everything to the right by 1 unit. And I get something that looks like this. Right. So again, this is the x-axis, this is the y-axis. There is no t-axis here. But I don't necessarily get this whole parabola. This is the graph of this equation. And anything on my curve has to also be on this curve. But my curve had this additional restriction that t is only allowed to run from -2 to 2. So then our question becomes, what portion of this parabola is included as a part of my parametric curve? You know, maybe I drop my ant right here at the vertex and I only let him walk to the right. Maybe I don't get any of this shit. Or maybe I drop him over here at the y-intercept and I let him walk to the left and I don't get any of this stuff. There's several ways to do this, and what WebAssign has you do is take your time domain and turn it into an x domain. So if I take my inequality for time, we know, or my inequality for the parameter t, we know that t is restricted to the interval -2 is less than or equal to t is less than or equal to 2, which means if I add 1 everywhere, -1 is less than or equal to t plus 1 is less than or equal to 3. And then t plus 1, oh shit, that's x. So this means -1 is less than or equal to x is less than or equal to 3. So the portion of this curve that I actually get is the piece from -1. So maybe from here all the way over to 3. So the piece of my curve that I actually get doesn't quite fit in what I've drawn here. So I'll redraw it. But it would go, 1, 2, 3. Yeah, really it's like just this part. Right? That's the idea. So rather than getting the whole curve, my parametric curve is just this. My starting point, or my initial point, it's right here. It's the point, what is it? It's -1, comma, -1 minus 1 is 4, x squared is 4. So this is -1, comma 4. And my terminal point is over here at 3, comma 4. And I've got this orientation. I started here, I drop the ant, he walks like this, and then I pick him up over here. So coming from the t inequality to the x inequality, in this case was very easy. Sometimes you'll have to think about it a little bit harder. But really, the thing you usually think of as your domain, the set of all the x values, is going to be the range of the x function as t runs over the specified time domain. So if you plug in -2, then you'll get out x equals -1. If you plug in +2, you'll get out x equals 3. And you know that this is a monotone increasing function. So the x's only take values from -1 to 3. Right? So one way to find these x values is to plug in the endpoints for the t values. That only works if the x function is monotone. But there's lots of ways to do it. And generally, once you have the picture, it'll be a lot easier. So graphing these is not hard. You can graph them by eliminating the parameter, as we did here, or just by making a table. What we would like to do is learn how to do calculus with them. So this is our intro to parametric curves, more or less done. One quick note before we leave. Last note from section 10.1. It's very easy to take an xy curve and parametrize it, especially if that xy curve is a function. If you want to come up with parametric equations for a graph of a function, you can always use x equals t and y equals f of t. So for example, I want to parametrize, that's the word, the verb, the graph of maybe y equals e to the x, where maybe -2 is less than or equal to x is less than or equal to 10. Let me swap those. How about, just for fun, -10 less than or equal to x, less than or equal to 2. That'll keep the graph size more manageable. So I can always do this by letting x just be t, and y, in this case, would be e to the t. Because definitely any points that satisfy this will show up here. And in this case, since x is just t, the t domain would be -10 is less than or equal to t is less than or equal to 2, because x, I'm picking x to be equal to t. The portion of the graph we would get is the mentioned one. We'll call this -10. This one, we'll call this here, right here, call this 2. So you have 2 comma e squared up here. And over here you would have -10 comma e to the -10. And the curve looking how you're used to exponential curves looking. All right, like this. So here we're able to come up with a set of parametric equations for this guy, just by using x of t equals t and y of t equals e to the t, because if x is t, then y should be e to the t. Another way to do this let's see. Simon, could I ask you to rephrase that question or maybe be a little bit more explicit what you're asking? I'm not sure I understand. So the function here was given, so to parameterize means to come up with a set of parametric equations whose graph is this. We know what y equals e to the x looks like. Can I come up with a set of parametric equations that will have that same graph? And the answer is yes. The easy way to do it. So here, f of x is e to the x. So the parametric equations t and f of t are just t and e to the t. So to parameterize is to come up with a set of parametric equations which will have that same graph. Yeah, so to parameterize y equals e to the x means to come up with a set of parametric equations which represents y equals e to the x, or which has the same graph as y equals e to the x. Another option would have been x equals the natural log of t and y equals t. Because here, still, y is e to the x. E to the x would be e to the ln of t, which simplifies to t, which is y. So if x is ln t and y is t, then e to the x equals y. Works the same way. Or I could have used x equals t cubed and y equals e to the t cubed, because this is still e to the this. There's other options. You can imagine there's actually infinitely many ways to do this. What else could we have used? We could have used x equals tangent of t and y equals e to the tangent of t, because again, this is e to the this. So each of these sets of parametric equations will have the same graph. These are all different ways to parameterize the curve y equals e to the x. The reason we do this, there's lots of them, lots and lots and lots of them, mostly for path integrals. So there are special kinds of integrals that you're going to meet in Calc 3, and if you take complex analysis, you'll meet them there, where you want to integrate some higher dimensional function. Think of it as like a rippling sheet, you know? And the way you do that, one of the ways to do that is to look at a path in the plane beneath the rippled sheet and imagine hanging a curtain down from that sheet and unwrapping it. I think the Wikipedia page on this has a decent somewhere here I'll find a good picture. There's nothing jumping out. Yeah, so I'll put a pin in that for just a second. I'm going to pause the recording. My vet is calling me back, so I'll be right back, guys. All right, so if you're coming back, I just got back from being on the phone with the vet, so I'm sorry I had to do all that. We were talking about parametrizations and why they're important. Simon asked the question, why do we care about parametrizing curves? The short answer is lots of reasons. The longer answer involves looking at things like path integrals. So in Calc 3, you'll want to integrate these higher dimensional objects. So your function here is this colorful rippled sheet. And we would like to know, how would I possibly find the integral of such a thing? Or what would it even mean to find an integral of such a thing? And the answer is you have to draw a path underneath it. That's why it's called a path integral, like that. So we're looking down from above. And then you imagine kind of hanging a curtain from your function down towards the xy plane, like so. And the area, that shaded blue area that's hanging from your path, that's the area we want. And so you'll learn how to do all of this in Calc 3, but the step that you need to get started is parametrizing that red path. So we saw that there are multiple ways to parametrize a given curve. We started here with e to the x, so my function f of x was e to the x. And we said the most natural way to parameterize it is to just let x be t and y be f of t. So the most natural one is this. And here we said we wanted x to run from -10 to 2, so t would run from -10 to 2 because x and t are the same. Another way to do that, I could have chosen x to be the natural log of t, my free choice. And then as t runs from e to the -10 to e squared, x will run from -10 to 2. And if I want this to be the graph y equals e to the x, I need y to be t, because then e to the x would be e to the natural log of t. E to the natural log of t is just t, and so that's my y. Other parameterizations which would be valid here, if I let x be t cubed, then I could pick y to be e to the t cubed. And then here my domains for t would be -cube root of 10 to cube root of 2. Or you could have let x be the tangent of t and y be e to the tangent of t. As long as y is e to the x, then you'll be on the graph e to the x. It's just a matter of what you choose for x and then making that fit the form, the shape. The calculus operations that we want to get practice with here, and I apologize, I did run through this with the kids that were there and I forgot to turn my recording back on, so I'm going to walk you through it slowly. So please bear with me. We want to answer the question, can we find tangent lines and areas with parametric curves? The answer to that question is, of course, yes. I wouldn't ask it if it wasn't. And the main formula you need for any tangent work is that dy dx is dy dt over dx dt. Remember, dy dx is the slope of a tangent line. That's the thing from Calc 1 that everybody remembers. And we just need a way to get that in this parametric setting. So if you divide top and bottom by dt, mathematicians hate that because dt is a differential, not a number. It works great though. You really should think about it as limits, but in the end it works just fine. So dy dt over dx dt will be your dy dx. So suppose I want to begin with the curve x equals cos of t and y equals sine of t, this set of parametric equations, and I want to find horizontal and vertical tangent lines. So I want to find any points where the tangent line is horizontal and any points where the tangent line is vertical. The thing to keep in mind is that as you're working with these derivatives, the variable you'll have to play with is t, which is not coupled in any obvious geometric way to the graph. So you'll be finding values of t, and you need to remember to plug those back into the original equations to find the corresponding points. Horizontal tangent lines are places where the slope of the tangent line is equal to 0. That's where dy dx, the original Calc 1 derivative, which is your slope of tangent line, is equal to 0. So to find horizontal tangent lines for this parametric curve, you need to solve dy dx equals 0, which means first you need dy dx, because I don't have that yet. I can't calculate dy dx directly because I'm not working with a y equals f of x situation, so I use the formula above. Dy dx, I know, is dy dt over dx dt, so I calculate dy dt. That's the derivative of my y function. My y function is sine t, so that's the derivative ddt of sine t, which is cos t. So dy dt is cos t. Similarly, dx dt is the derivative of the x function. The x function is cosine. So dx dt is ddt of cos t, which is negative sine t. So dx dt is negative sine t. Dy dt is cos t, which means dy dx, the derivative I'm looking for, is dy dt over dx dt, cos t over negative sine t. So if I want to find horizontal tangent lines, those will be places where dy dx, this thing, is equal to 0. How can something like this be equal to 0? Well, it's a fraction. So fractions are 0 when the top is 0 and the bottom is not 0. So you want to find any t values that make the top 0 and then check and make sure they don't also make the bottom 0. If you happen to find a t value that makes both of these 0, then you need to take a limit and use L'Hopital's rule to figure out what's really going on there. But for us, here we're lucky. So when is dy dx equal to 0? Well, that's when this fraction is equal to 0. And that will be true as long as cos t is 0. So we set the top equal to 0, like I just said. Cos t is equal to 0 at pi over 2 and 3 pi over 2. There's infinitely many places where cos t is equal to 0, but I'm going to look just on the interval 0 to 2 pi. So the solutions are pi over 2 and 3 pi over 2. And if I want to find the corresponding points, I plug those t values back into the original functions. So my vet is calling again. I have to pause one more time, sorry. Okay, sorry, so my vet just called me back. I have to go pick up my dog in a few minutes. So these next few bits are going to be a little bit rushed, and I apologize for that. Horizontal tangent lines, places where dy dx is 0. Dy dx is cos t over negative sine t, so that will be equal to 0 when the top is 0, which happens at these t values. We plug these t values into the original xy equations. To find the points. So x at pi over 2 is cos of pi over 2 is 0, y at pi over 2 is sine of pi over 2, which is 1. So you get the point 0, 1 by plugging these t values in, and you get the other point 0, negative 1 by plugging that t value in. Vertical tangent lines were what we went after next. And we found those vertical tangent lines is what we went after next. And those are places where the derivative dy dx that defines the slope of the tangent line gets big. So you'll have horizontal tangent lines when dy dx is 0, and vertical tangent lines where dy dx blows up to infinity. So dy dx, that doesn't change. That's still cos t over negative sine t. And we need to figure out where that blows up to infinity. Functions blow up to infinity when the bottom goes to 0. So we set the bottom equal to 0. And we get these solutions for t, 0, pi, 2 pi, because that's where sine of t is equal to 0. And then we plug those in to get the points. So if I plug in t equals 0 to both x and y, I get cos of 0, which is 1 for the x, and sine of 0, which is 0 for the y. That's the same point we would get when we plug in t equals 2 pi, because cos of 2 pi and cos of 0 is the same, sine of 2 pi and sine of 0 are the same. So these two t values give me the same point. I have a vertical tangent line here. My other vertical tangent line comes from plugging in pi. If I plug in pi to the x function, cos of pi is -1, so that's this -1. Sine of pi is 0, so that's this 0. And those are our vertical tangents. If we think about it, we could have guessed this by eliminating the parameter and graphing the curve. So just like we did for the ellipse example earlier, cos squared plus sine squared, that's the same as x squared plus y squared, because x is cosine t and y is sine t. So this guy is a regular rectangular equation, x squared plus y squared equals 1. It's the unit circle. So of course I have a vertical tangent line here and here. And of course I have a horizontal tangent line here and here. I do have to go collect my dog from the vet now. So there are a handful of examples of things that I go over after this. We talk about how to find areas, and we also talked about how to find arc length. The area stuff, I have on the back of one of these, I think. Yeah, here. Everything works just like it does in the normal case, where y is a function of x. So if I want to find the area under a parametric curve from t equals a to t equals b, these are not x values, these are t values, then what I do is I imagine, your normal Riemann sum stuff. So I get a rectangle here whose height is determined by y, and whose width is determined by x, it's dx. Dx though, because x is a function of time, dx is x primed of t times dt, where x is your function. So you've got your two parametric equations, x and y. Dx will be x primed of t times dt, or you could think of this as like coming from the dx dt calculation. So I do an example where we find the area enclosed by an ellipse. We just plug into this formula, take this formula. I want to find the area enclosed by the ellipse from the earlier example, whose parametric equations were x equals 2 cos t and y equals sine t. I calculate dx by finding dx dt, and then multiplying both sides by dt, just like you started finding differentials at the end of Calc 1. So dx is -2 sine t times dt, and y is just sine t. So I plug those things into this formula. Remember, we talked about orientation, the arrows along the curve, the direction the ant is walking. Here, we're actually walking from right to left. We're going like this. So we're walking over this backwards. So this orientation pointing right to left tells me that my integral is actually going to come out negative. And that's okay. I just have to remember that when I get the area bounded under this curve from 0 to pi, it's going to come out negative because we're walking backwards. And it's going to be half of the area of the ellipse. So if I want the whole area, I have to take whatever I get for this integral, make it positive, and then double it. This is 2 times sine squared t, so we use our half angle formula. Then we integrate like we did way back in chapter 7, and I get negative pi. So I make that positive, that'll be positive pi, and then I double it to get the whole area, and I'll find that the area enclosed is 2 pi. And that's pretty much the whole area thing in parametric curves. It's not super exciting. You just need to remember this formula and the subtle things that can happen with orientation. So draw your picture first. And if your arrows are going right to left for a portion of that integral, remember that you're going to get the negative of the thing you want. The last thing we talked about was arc length. And this is a little bit complicated. What I did here is I went through the derivation of the arc length formula because it's a lot of fun. You take your parametric curve and you chop your t interval up into a bunch of little pieces of equal length. And then for each of those t values, you drop a point. So I've got P0, which is associated with t equals a, P1, P2, P3, P4, all the way up to, I call this Pi minus 1 and this Pi. And then we keep going, I call the last one Pn. So then the length of the straight line joining P0 to P1 or P1 to P2 or Pi minus 1 to Pi in general is the hypotenuse of this little right triangle. And I can calculate that. Here's the length from Pi minus 1 to Pi squared as delta xi. I call this delta xi because it's the delta x associated with the I points, and delta yi. So Pythagoras says that the hypotenuse squared is this squared plus this squared from the picture. So I take square roots on both sides, and then I multiply by dt over, or delta t over delta t. The delta t from the bottom, I shove into the square root as delta t squared. The delta t from the top stays outside. And then I distribute this 1 over delta t squared over these, and I get this. So you're going to want to watch this slow or pause, take your time, write your notes. That's the length from Pi minus 1 to Pi. So the total length will be what I get when I sum all of those. So usually we use the symbol S for arc length. Your book sometimes uses L. It's the sum of all the little lengths. And according to the algebra work we did above, each of those little lengths looks like this, so the sum looks like this. So each of the little lengths looks like this, so all the length is the sum of the little lengths. And we recognize this as a Riemann sum. This is the Riemann sum for this integral. Right? Delta t becomes dt, delta x over delta t becomes dx dt, delta y over delta t becomes dy dt. These guys are still squared, they're still added up, and they're still under a square root. The integral is running from a to b. So the exact length of the curve, the parametric curve, x equals x of t, y equals y of t, from t equals a to t equals b, is this guy. So this is what you need to remember from the arc length stuff. I did do a calculation. We found the length of this guy. This guy is an Archimedean spiral. These parametric equations look a lot like the parametric equations for a circle, except I've got this t out front. And if you look, Desmos is good at graphing these. You just have to graph them as ordered pairs. So if you go from 0 to 1, it looks like this. 0 to 2 pi looks like this. 0 to 4 pi looks like this. 5 pi. So it's a nice spiral. Nice spiral where the radius increases at a constant rate. Those are called Archimedean spirals. So this is an Archimedean spiral that we're finding the length of. These are the parametric equations. So my length should be the integral from 0 to 1, dx dt squared plus dy dt squared. Dx dt is here. I calculate it using the product rule. First I differentiate the t, I leave the sine t alone. T differentiates to 1, so I just get sine t. And then I add that to what I get when I leave the t alone and differentiate sine. Derivative of sine is cosine. Same thing for dy dt. First I differentiate the t and leave the cos alone. That gives me 1 cos t. Plus, then I leave the t alone, differentiate cosine. Derivative of cosine is minus sine. So this is cos t minus t sine t. Plugging these guys into these, my integral becomes this. And this becomes huge. So I need to FOIL each of these out. And I get this. I'm writing the square root now as the 1/2 power because I don't want to draw a ginormous square root. But luckily, after you FOIL this out, so this first piece FOILs out to these. Sine squared plus 2 sine t times t cos t plus t cos t all squared. So this is my firsts, my inners and my outers, my lasts. Similarly, this foils out to this. You'll want to pause and check the algebra. My firsts minus my inners and outers here, and then my lasts. And then you can see how I've underlined these things. That was to help me group. So I see sine squared plus cos squared. That's going to be 1. The squiggly underlined things cancel exactly. Plus 2t sine t cos t minus 2t sine t cos t. So those add up to this 0. And then the bracket underlined things, these guys, that's t squared cos t plus t squared sine t. I can factor out a t, and I get cos squared t plus sine squared t. Those add up to 1. So this piece is 1. So altogether, I get the integral of the square root of 1 plus t squared. Looks like this. If we rewrite that as the square root instead of the 1/2 power, you're more likely to see what to do. This is a trig sub problem. It's a tangent sub. So I let t be tan theta. dt is secant squared theta d theta. I change my variables and my bounds. 0 stays 0, but 1 becomes pi over 4. So if you forget your trig sub, it's a good time to refresh it. The integral becomes this, which is everybody's favorite secant cubed. Secant cubed requires looping IBP. It comes out to 1/2 secant tangent plus the natural log of secant plus tangent. So I get that evaluated from 0 to pi over 4. I'll let you do the evaluation. When you plug in 0, this is the natural log of 1 plus 0. Natural log of 1 is 0. And this is 1 times 0. So the lower bound contributes nothing. Everything is 0 there. The upper bound, the secant of pi over 4 is root 2. The tangent of pi over 4 is 1. And then you have the natural log of secant plus tangent. So it'll be natural log of root 2 plus 1. So this is how that all comes out. I'm sorry this is a little bit rushed, but I got to go grab my dog now. So I'm going to stop recording. I will see you guys in the office hour. I'm going to do an extra office hour tomorrow to make up for the one I missed today, and then in class on Wednesday.